Hi, I'm Sam Wong. This is Lab 3 for Physics 2211, in which we're looking at parallel and perpendicular force. These are components of the net force, and as I mentioned earlier, there are two different components. The parallel component of force is dictating the magnitude at which a system is going at, and the perpendicular component is related to the curvature of the system's path. This is also seen in momentum, as there is a perpendicular momentum and a parallel momentum, and this is due to Newton's second law, as net force equals the change in momentum over change in time. This is important to understand for many careers, especially astrophysics, as we'll see later, as you can use it to track solar systems and how we actually launch our satellites to make sure that none of our satellites actually crash into one another. The experiment we had for this lab was actually a code-based simulation in which we were analyzing a black hole and a star that is moving about it. And the problem we had to solve was finding the mass of the black hole based on that star's trajectory. The given information we had was the fact that the gravitational force of the black hole acting on the star is the only force upon the star. Therefore, we know that there's no planets or asteroids nearby that is affecting its trajectory. The mass of the star is 2 times 10 to the 30th kilograms. The star had a unique trajectory about the black hole. The black hole is the origin point for the graph of which we analyze position. So you know that the radius is just the star's position. And delta time is in 1 day in seconds, so it's 60 seconds times 60 minutes times 24 hours. In solving this problem, I'm going to show you a little bit of my thinking process as far as the mathematical and algebraic side of things. So we know that the net force is equal to the change in momentum over change in time, and since the gravitational force is the only force in the system, we know that the net force must equal the gravitational force, and we also know that the parallel plus perpendicular force components of F net must equal F gravitation. Since gravity is the only force and there's only one force, we know that the momentum components are also equal to the force components. Therefore, momentum parallel is equal to the force parallel and perpendicular. And we know how to find the perpendicular and parallel components of momentum as identified as these equations right here. This is the gravitational equation right here with ms representing this mass of the star, and this is the mass of the black hole. And using this equation with these equations, we can find the mass of the black hole is equal to the force perpendicular times the radius squared, all divided by the gravitational constant times the mass of the star. We use the force perpendicular magnitude because the gravity is acting perpendicular to the star that is moving around, because it's altering its curvature and is not necessarily affecting the magnitude of the force. In saying this, we had to plug this all into the code, so let's go through the code to show you what I was doing. So here we have the mass of the star plugged in. We also have delta t plugged in as the 60 seconds times 60 minutes times 24 hours in the day. We can scroll on a little bit further and we'll see the P initial and P final for momentum are just equal to the star times the velocity of initial and final. We have the change in velocity and change in momentum right here. And this is where we calculate that net force is equal to the change in momentum, which we found up here because of Newton's second law. We have the calculation for the parallel component of the vector, so we have p hat right here on the magnitude of p final minus magnitude of p initial over delta t for the magnitude of the parallel component, and the parallel component is just the multiplication of those two, which is actually just equal to the net force right here, or the net force parallel. And then we have the perpendicular, for us to make it easy, it's just the change in momentum minus the change in momentum times the parallel component, and that's equal to the F net perpendicular. And here's where we plugged in the equation we saw on the slide. We have arrows dictating the F net, which is going to be shown through the simulation. So let's run the simulation. Here we are. We have F net always pointing towards the star because the net force is the gravitational force. We have the perpendicular component being the blue one, and there's actually a black vector. If I can show you again, the black part right here is the parallel force components. And as you can see, the mass of the black hole is just flashing by as it keeps calculating it over and over on the loop. And these are the total magnitudes for the components. All right, here are my results for the simulation. As you just saw, since the mass varied during the whole entire simulation, as you saw it's running underneath, I just happened to use the average mass, which is just the addition of the max mass and the minimum mass divided by 2. These are the numbers, so I got about 1.77 e to the 34th kilograms for the black hole's mass. As I just said in the results, the mass was varying throughout the whole entire simulation, which led to a possible discrepancy that I could find. There aren't many because it is a code-based project, but I did find that the simulation was setting a predetermined trajectory for the star, which means that the path the star followed didn't exactly follow the true scenario of the problem, in which the gravitational force was the only force acting on it. So this resulted in the mass readouts varying because the distance from the black hole wasn't proportional to the actual distance it should have been for the gravitational force to be the only force there. Now, what does this lab actually mean? Does it mean that momentum and net force are the same exact thing? No. Net force is the thing that causes momentum to change. So these are sometimes invisible forces that you can't see, but you will always see the change in momentum because it's the observed effect of these net forces. And sometimes even net force and momentum are pointing in different directions, i.e. when an object is slowing down. And the reason why momentum and net force are very closely paired is because the components of the net force are related to the components of momentum via Newton's second law. Therefore, they're very close related, but in reality, there are many different forces that can contribute to the net force, but these are all only contributing to one change in momentum, because momentum is there's only one momentum per system, and that's the only thing that you can observe from the net force. Now knowing this, we can answer the what if question of the week. What if we had the technology to suck up that black hole in the simulation, throw in a different one? What if we saw the star travel around the same trajectory as before? This would mean we would know that the new black hole would have the same exact mass as the black hole we had just removed. This is because the force of gravity varies due to mass and distance. Therefore, if the distance is constantly the same distance on the trajectory as before, that would mean that the mass would have to be the same exact mass as the black hole before. And that would also mean that for this lab overall theme, the net force is still equal to the same perpendicular and parallel components.